This is lesson 8.5. This is the law of sines and cosines. Let's go ahead and pray, and then we'll start the lesson today. Father in heaven, thank you for your kindness towards us in Jesus Christ. Thank you for your mercy. I thank you for the student you've given me, whoever they are and wherever they are today. I pray that you would bless them. Help them bless your name, because your name is worthy. Help me to explain the law of sines and cosines today in a way that's understandable to my student, in a way that my student can learn and succeed, and in a way that my student will have the skills they need to be able to use the law of sines and cosines so that they'll know it completely and they won't need any further lessons on this particular topic. We thank you for what you've done in Jesus Christ. We give you praise. In Jesus' name, amen. All right, this is the law of sines and cosines. So we're going to start with a question. Is it possible to solve unknown measures in a triangle if that triangle is not a right triangle? That's a good question. It's an important question because so far trigonometry has only given us the tools we need in order to solve problems concerning right triangles. But there are infinitely many other kinds of triangles out there, and many triangles are not right triangles to begin with. Well, the answer to this question is a resounding yes. There is a way. There are two laws that we're going to learn today that are applicable not only to right triangles, but to all other kinds of triangles. And we're going to learn how to use these laws appropriately and how to use them to solve correctly and clearly the problems that we're going to be given. So let's go ahead and begin with the following situation here. Here is an obtuse triangle. The measure of angle C is larger than 90. The lowercase letters represent the side lengths, and the uppercase letters represent the angle measures. First, we're going to draw an altitude and label its length as h. Next, we're going to subdivide side C into x and y. So, the following formulas are now true because we have two right triangles. So, let me try to get this on the same screen. Look at the sine of angle A. Sine is defined to be opposite over hypotenuse, so that's h over b. Look at the sine of angle B. That's h over a, opposite over hypotenuse. So using cross multiplication, I now know that h can be written as b times sine a, and h can also be written as a times sine b. Now I'm going to use the substitution property. So since h can be represented as two different things, I can say that b times the sine of a is equal to a times the sine of b. I'm going to divide both sides by AB, and I get the sine of angle A over side A equals the sine of angle B over side B. And this is one part of the law of sines. Now I've got to figure out how to work the sine of angle C into this. So, okay, we're going to take our triangle that we just had up above, and we're going to rotate the triangle so that BC is the base. Let's scroll back up. Look at the triangle that we have. We're going to rotate it this way so that BC is the base. We draw altitude AD and give it a measure of J. Notice that because C is an obtuse angle, J is outside, the altitude is outside of the triangle, and we learned this in a previous lesson. Now, when the angle is obtuse, then the opposite side is outside the triangle. And that means that J is considered the opposite side measure to the angle C. So the angle being obtuse means that the opposite side is actually outside of the triangle. And that B, right here, is considered to be the hypotenuse. See, in a triangle that has an obtuse triangle, this triangle, ABC, is not a right triangle. So because C is obtuse, it reaches outside, and so the right triangle is actually here. It's external to the triangle. J is the opposite, B is the hypotenuse. this means that the sine of c over 1 is j over b. And so j can be written as b times sine c. But if you look at the sine of angle b right here, we can also write that as j over c, because we have this larger right triangle here, BDA, and so j over c. So I can find two expressions for j, and so substitution allows me to say that b times sine c equals c times sine b. Divide both sides by bc, and we get sine of c over c equals sine of b over b. And now we have the law of sines, which says that if I have a triangle, ABC, the sine of angle A divided by side A equals the sine of angle B over side B equals the sine of angle C over side C. And it's also true that the reciprocal relationships hold as well. So side A over sine A equals side B over sine B equals side C over sine C. And the cool thing about the law of sines is that it works for all triangles, not just the right triangles. Let's go ahead and look at using the law of sines. Find each measure, round lengths to the nearest tenth, and angle measures to the nearest degree. I want to find the measure of m of ft, which we're going to call little m. So I know angle m is 35 degrees. I don't know little m, which is ft. I do know f is 108 degrees, and I know that little f is 20. That's the side. So I use the law of sines. The sine of 35 degrees divided by m equals the sine of 108 divided by 20. Now we do our cross multiplication. 20 times the sine of 35 degrees is equal to m times the sine of 108 degrees. Divide both sides by the sine of 108 degrees. And so 20 sine 35 degrees divided by sine 108 is approximately 12.1. And now I know m, which means I know side ft. Let's find angle t. Well, I know that the sum of all three angles in the triangle is 180 by the triangle sum theorem. And now I just substitute 35, 108, plus the measure of angle t is 180, and that makes angle t equal to 37 degrees. Now let's solve for little t, which is this side right here, which could also be called side MF. We write the sine of 108 degrees over 20 equals the sine of 37 over t. Cross multiply. T times sine 108 equals 20 sine 37. Divide both sides by sine 108, and we get 12.7. And now we know all of the angles and all of the sides in the triangle. And once you know all of the angle measures and all of the sides, the triangle is solved. There's nothing more to solve for it. Now we have a new goal. Can we find a formula that uses only the three sides and one angle? So we're going to try and develop the law of cosines. And what's more important to me right now is that you understand how to use the law of sines and the law of cosines. It's not so important to me right now that you know how to derive them like we're going to do. I'm going to show you how it all comes together. But this particular process that I'm going to use today is very algebraic. And so if I lose you in the process of how to get the law of cosines, I want you to know that that's okay, because I really want to teach you later on in the lesson how to use the law of cosines. But I didn't just want to tell you, okay, here's the law of cosines, let's use it. I at least wanted to take a shot at trying to show you how we're getting it. So that's what this part of the video is all about, to at least try to show you how we're getting the law of cosines. So, okay, here's triangle ABC, and we've portioned it up in this way. H is the altitude, X plus Y is the longer measure C. Now this triangle that we have here isn't necessarily a right triangle, But the goal is to get a formula that uses only little a, little b, little c, and then one of the angles, either A, C, or B. And the angle that I've chosen is angle A. So let's begin. Down here, we can say that the cosine of angle A is adjacent over hypotenuse. That is to say, x over b. Now, what I'm going to do with that is I'm going to multiply the top and the bottom by what's called a glorified 1. 2 times x plus y over 2 times x plus y. Now, I'm going to take the bottom, x plus y, and from the picture, I can see that x plus y is the measure c. So the bottom is going to become 2bc. But I'm not going to do that to the top, and the reason why is because it makes the algebra work really nice. So I'm going to distribute 2, and I'm going to distribute x into the top. So I get 2x squared plus 2xy. Now I'm going to separate, I'm going to do two things actually. I'm going to separate the 2x squared into x squared plus x squared. And I'm going to add a 0 in the numerator like this. So here's x squared at the beginning, here's x squared at the end. So there's my 2x squared. And then I've added in y squared minus y squared, which is the same thing as adding in 0. But what's going to happen is that I'm going to shuffle my terms around. So I'm going to shuffle these last two around to become x squared minus y squared. And then x squared plus 2xy plus y squared actually factors into a perfect square trinomial. So that's x plus y squared. And remember, x plus y is the same thing as c squared. Now I'm going to do this adding 0 thing one more time. So I'm going to throw in an h squared minus h squared. And so now I have x plus h squared, which if you look from the triangle, x squared plus h squared is equal to b squared. And y squared plus h squared is a squared. And so now that leads me to this conclusion down here. I can replace this part with b squared, and I can replace this part with a squared. So now I have c squared plus b squared minus a squared over 2bc is equal to cosine of angle A. Now I multiply the 2bc up to the other side, and I have 2bc times cosine angle A equals c squared plus b squared minus a squared. I multiply both sides by a -1 because that's going to make the formula look like the way that I want it. So negative 2bc times cosine A is now equal to a squared minus c squared minus b squared. And now I add c squared and b squared to the other side. And so there's the final answer. This is the law of cosines. A squared equals b squared plus c squared. Looks kind of like the Pythagorean theorem, doesn't it? Then minus 2bc times the cosine of angle A. That's the law of cosines. That's the derivation of getting the law of cosines. But now here comes the important part. I'm going to show you how to use the law of cosines. So the law of cosine says in a triangle ABC, you can write 3 different formulas if you want. All 3 formulas hold true. You can say c squared equals b squared plus a squared minus 2 times a times b times cosine c. You could say b squared equals c squared plus a squared minus 2 times a times c times cosine b. Or you could say a squared equals c squared plus b squared minus 2 times b times c times cosine a. Now, the law of cosines actually isn't 3 different equations. You can write 3 different equations using the law of cosines. I prefer the worded form of the law of cosines more than I actually do the formulaic form. But if you want to just memorize the formulaic form, that's okay. But the word form is more clear. It says this: the square of any side of a triangle is equal to the sum of the squares of the remaining sides minus twice their product times the cosine of their intended angle. That is the angle between the 2 remaining sides. And so the worded form is actually the essence of the law of cosines, whereas the formulaic form just writes out the 3 different possible ways you could use the law of cosines. All right, so now let's look at a specific example of how to use the law of cosines. My goal is to solve the triangle, and that means I want to know everything I can possibly know about the triangle. So what I do is I write down the following. I say a squared is equal to 10 squared plus 12 squared minus 2 times 10 times 12 times the cosine of 28 degrees, because that's the angle that's between the two sides. Now I just use my calculator. I punch all the numbers in the calculator and I get this 32.09257771. And then I take the square root. And so A is approximately 5.67. Now I know side A using the law of cosines. And here's the really cool thing. You only have to use the law of cosines once. After you use the law of cosines, the law of sines can be used to figure out everything else. So now I take that same picture. Now I'm going to use the law of sines to figure out angle B. So the sine of 28 degrees over 5.67 is the sine of angle B over 12. Cross multiply the 12 up here, and I have 12 times the sine of 28 divided by 5.67 equals the sine of B. Now we use the sine inverse to figure out angle B. So the sine inverse of 12 times the sine of 28 degrees divided by 5.67 equals angle B. And so B is approximately 84 degrees. Now I think it's going to be a great idea if I just take a moment, open up my calculator program, and I'm going to show you how to do that right on your calculator. So let me go ahead and clear out what I need to do here. Let's just check to make sure my calculator's in degree mode. It is. Good. All right. All right, let me try to show you now how you would calculate this. So first, second sine inverse. There's your sine inverse with an opening parenthesis. 12 sine 28. Then I close the parenthesis for that particular sine. Divided by 5.67. And then I close the parenthesis for the sine inverse. Hit enter. And remember, when we're finding degree measures, we're rounding to the whole degree. And so I'm going to say 84 degrees. And that's how you calculate this using your calculator. Let's figure out angle C by using the triangle sum theorem. Measure of A plus measure of B plus measure of C is 180. Substitute in what we know and subtract. So the measure of angle C is 68. And again, once you know all of the angle measures and all of the side measures, the triangle is completely solved. Example 3, using the laws to find the angle measures. So, okay, I want to figure out angle B. So I'm going to use the law of sines. The sine of 40 degrees over 10 equals the sine of B over 12. I cross the 12 up to the other side, and I have 12 times the sine of 40 equals, or over 10, equals sine of B. Now I use the inverse sine to figure out angle B. So inverse sine of 12 sine 40 degrees over 10, and that's going to be about 50 degrees. And if you want to pause the video and try this again just to verify that you get that, that would probably be a good idea. Let's go ahead and find the measure of angle A. And look at this triangle we've got. We know all of the sides, but we don't know any of the angles. Now, I want to find angle A. So that means I'm going to begin the law of cosines with the opposite side squared. So because I'm looking for angle A, I'm going to start with 15 squared. So 15 squared equals 18 squared plus 8 squared minus 2 times 18 times 8 times cosine A. Now, I could start plugging things into the calculator here, but I'm not going to. I'm going to keep things in their simplest form. So I'm going to subtract 18 squared and 8 squared to the other side. And that gives me 15 squared minus 18 squared plus 8 squared. I divide both sides by -2, 18 times 8. And so that gives me the numerator divided by -2 times 18 times 8. And so since I have negatives top and bottom, I'm going to now rearrange things. So that's the same thing as multiplying the top and bottom by a -1. So now the top becomes 18 squared plus 8 squared minus 15 squared over +2 times 18 times 8. And now I'm going to use the cosine inverse to figure out angle A. So now let me go ahead and show you how to do this on your calculator. Let's clear out the window. Let's pull that in. Here we go. This is what you do. Second, cosine inverse. Now another beginning parenthesis for the numerator. 18 squared. And then plus 8 squared minus 15 squared. And then close the parentheses. So that closes the numerator. Division symbol. And now a parenthesis that begins the denominator. 2 times 18 times 8. Close the denominator and then close the inverse cosine. So we're about 55.5, which is about 56 degrees for the inverse cosine. Example 4, astronomical application. On a certain date in history, the distance between Earth and Mars was 99.3 million kilometers. The asteroid was recorded as 121 million kilometers from Earth, and the angle between EA, that's Earth and asteroid, and EM, that's Earth and Mars, was 36 degrees. How far apart was Mars and the asteroid on that day? In other words, what is the measure of angle that's the first question, how far apart? So what's the distance from A to M? The second question is, what's the measure of angle EAM? So what's the measure of this angle right here, Earth to asteroid to Mars? First thing we're going to do is we're going to use the law of cosines. So we're looking for the distance from asteroid to Mars. So AM squared equals EM squared plus EA squared minus 2 times EM times EA times cosine 36. Plug all that into your calculator and then take the square root of whatever you get. And so we can say the distance from asteroid to Mars was approximately 71.14 million kilometers on that day. Make sure that when you're doing a word problem, you end with a sentence. Then we take the sine, we're going to use the law of sines. So we do the sine of 36 over 71.14, that's the value we found, equals the sine of angle EAM over 93.3 million kilometers. Cross the 93.3 up. Take the inverse sine of both sides to figure out the measure of EAM. So the sine inverse of 93.3 over 71.14 times the sine of 36, all of this is inside the sine inverse, is going to be approximately 55 degrees. And so that means that this angle right here is about 55 degrees. And that solves the problem for now. If we wanted to, we could easily take 180 minus this to figure out the angle, but that wasn't asked of us. Finally, there are situations when you must use the law of cosines because the law of sines does not solve the problem directly. And so there are two cases pretty much when you want to use the law of cosines. What are the two cases? The first case is when you know all of the sides but none of the angles. If you get a triangle where you know all of the sides but none of the angles, that means that the law of sines will not give you what you need yet. So you have to use the law of cosines. That's the first case. The second case is when I know two sides and the intended angle only. I don't know the opposite side and I don't know the other two angles. So if I only know two sides and their intended angle, that's the second case when I have to use the law of cosines. As we study trigonometry, we learn new tools to solve what used to be very difficult problems. Just think about that. Not only has God written mathematics into all of his creation, he has also given us the very means where we can come to understand that creation and give him praise. My God, how great thou art. Give Psalm 104:1 a read. All right, that is the lesson on the law of sines and cosines. God bless you wherever you are today.